very happy to be here. Welcome for introducing me. So I'm going to talk about going from data to insight using multimedia analytics. And if we see what happened over the last 20, 25 years, well, a little bit more, 30 years, it's just a very short time, you see how much information we have gained in terms of multimedia. I was a PhD student in 93, I graduated in 93. That was when the World Wide Web started. Just before that, the World Wide Web didn't exist. Well, look now, everything is on the web. We have YouTube, we have Instagram, and we have a huge amount of multimedia data that we can work with. But we cannot do it ourselves. We need tools, we need AI tools to do the analysis for us. And that's what we're going to talk about in the beginning of this presentation. So in 2000, so 24 years ago, we wrote a, by now, rather famous paper, has a lot of citations, on what was the state of the art at that moment in doing multimedia analysis, and especially in content-based image retrieval. I can tell you at that moment, it was all very poor. The quality of what we could do was very, very low. And the reason, what we called it at that point, was the so-called semantic gap. So humans saw a picture, had an immediate understanding of it, was very good at understanding what it was, and the machine just sees pixels, just sees a set of numbers, a very difficult way to work with. In the days, that was really a challenging problem. Just recognizing a cat or a dog, the canonical example, on a picture was already extremely difficult, and most of the time we did it wrong. If you now look what happened, so very recent, 2021, clip from OpenAI came along, and they did two very interesting things. One thing they did, they took almost all the data from the web that was available. Took an image and its corresponding alt text, so its description for people that could not see the picture, and assumed that this combination was most of the time correct. And if you had a picture and you had a description from another image, then most of the time that would be wrong. So in that way, they could do a self-supervised learning, and they learned from this huge amount of multimedia data, image data, text data, to learn what was on the picture. That was one thing they did, and what they managed to do, you do this task, you're very good at combining the text and the image, and it turned out that you could do a lot of tasks, what they call downstream tasks. So other tasks than the one that the system was trained for. So how did it perform? They worked on ImageNet, where at that moment was the benchmark to work on. And with this completely self-supervised method, they won from all the methods that were hand-labeled by humans. So a big difference to what we had before. And they could do a lot of interesting tasks with it. This was one that was already well, I saw it yesterday in one of the presentations, visual question answering. Well, look at the first picture. What is the moustache made of? A very important question to know what is this woman having as a moustache? And the other questions that you can look at. Visual entertainment. What can you say about this picture? Well, two women are holding packages. Yeah, that is correct. The sisters are hugging goodbye while holding to go packages after just eating lunch. Well, you cannot see whether they're sisters, but at least it's not wrong. And the men are fighting outside the daily. No, that's wrong. You know for sure that that's not the right answer. Another one, more reasoning, and that was also a topic that came back yesterday. Can you reason about this image? Can you answer questions like, is the ball to the right of the green apple? Questions on those particular images. And it turned out, as I said, clip made a revolution. Trained on this combination of text and images, it could also do these kind of tasks and outperform the existing methods. So if we look at the status of multimedia analysis now, we have come a long way from where I started, where we are now, basically during the era of deep learning. So AI brought a lot there. We used to design features by hand. Now you train them and you learn them all via the computer. People started with convolutional neural networks. We were talking about it yesterday, but now everything is a multimodal transformer and moving into foundation models, as they are called. So very, very big models which can do a task, and you use them to do other tasks. And very important, we went from supervised, where you label things, to unsupervised learning. And CLIP, but now also Gemini, GPT-4, all the kind of foundation models, they made this happen. And the quality is improving still by using larger models, more data, and the semantic gap is kind of solved. Not completely, but it's kind of solved. But what you see, all those things are analyzed on benchmarks. So how well can I classify something? And I have a number getting as an output. So let's look at some example applications that we are working on in our group, and how, well, you will see later what we're doing. One thing we did was analyzing discussion forums. So this was Stormfront, which is a very nationalist platform. It actually has been brought down now. And we wanted to know, what are people saying there? What kind of topics are they posting? What is, are there signs of radicalism? Those kind of things. Looking at greenwashing, also a topic that came back yesterday. There are a lot of companies now who pretend to be very green and very environmentally friendly. Look at this nice picture of an airplane. You don't even see the airplane, but it's there. That's the kind of commercials that you see. Well, very much away from the fact that, of course, flying is not a good thing. Many of us came here flying, me too. But companies try to greenwash on that. And we created a big data set where we actually have this data from all the tweets that a company has, and try to see whether we can connect it to ESG measures, for which there are actually websites where you can get information for every company, how green they really are. And now the question is, can we actually get a link between the data and how well people say that these companies are doing in terms of greenwashing? Another one, and we'll come back to that one later, you see a lot of deepfake videos currently on the web. Videos that are not real, created by a system, and the creation is getting better and better and better with the new foundation models, but they are not real. So how can we use those? Well, how can we deal with those? How can we detect what is happening there so that they are accepted as real videos? And the question is multimedia analysis enough for such applications? Yeah, I showed what we were doing. Is that enough? Well, if you look at the professional user that is doing the kind of applications that I just showed, and all kind of other applications where images play a role, they don't really care whether performance is 85.4 or 85.9. Well, if you look at the AI community, if you go to conferences like CVPR or NeurIPS or all the others, that is what people are doing at the moment. Tweaking this little performance improvement that they can make. You have in the field a lot of real-life benchmarks. Well, if you look at the real-life benchmarks, they're not that real-life. They're not really questions that we, if you are a professional, really are dealing with. They're interesting, challenging, but not what we really need. And if you look at the downstream tasks, well, if you look at this example of the girl having bananas as a mustache, do we care? I mean, if we look at the image, it's very clear that she has bananas there. So why would we need an automatic system to tell us that? So many of the tasks that are there are not what we actually need. So already in 1962, so even before I was born, this person, Richard Hamming, very famous person, at that moment already said, the purpose of computing is insight, not numbers. And we are still, with a lot of the things that we're doing in AI, we are looking at numbers. So what is insight? And that's the problem. Insight is actually something that is not easy to define, actually very difficult to define. Chris North already a long time ago at least made an effort in doing so and said, well, it's complex, so you need all kind of information sources before you can really get insight in your data. It is something that builds up over time. So it's not like you look at your data, you look at your image, and now you have the answer. No, you have to have multiple images, multiple text, combine them, and then on top of each other, what you learn, you get to a final solution. It's not something you can describe in a benchmark as a number. No, it's something that is more qualitative. It's something that you don't know. Well, if you have a benchmark, you already know what the outcome is, so that can never be really insight. And it has to be connected to the domain that you work in. Again, something benchmarks typically don't do. And that is what people took as a starting point to start the field of visual analytics. So this is the basic model from Daniel Keim in Constance. You have data, you have visualizations, and you have models, and they all are interacting. You go through interactive processes to get to knowledge. To get to knowledge, insight, both have been used there. And that is a very simple model. So 8 years later, actually from the same group, Sasha et al., they added other components to the model to bring it into something where the computer is part of the model and the human reasoning, the human interaction is also part of the loop. So the whole sense-making loop, all the interaction that is there is part of this model. And they work on, well, basically numeric data. That's how those models started. So what is multimedia analytics? That's the topic that I was saying I'm going to talk about, topic of our work. And that was defined in 2010 by Chinchor in a interesting paper, a special issue on the topic, where they said, well, multimedia analytics is the combination of multimedia analysis plus all the things we can do in visual analytics. So that was our starting point. We now have it a bit more elaborate. Multimedia analytics is the science of analytical reasoning supported by a combination of AI techniques for getting the richest information possible from the multimedia data, visualizations providing instant insights, and interactions surpassing human and machine intelligence. We're kind of ambitious, but that's what we try to do with our work. So at that time, so the same time that this model from Sasha came out, we worked on the multimedia part, made a big survey on looking at that. And we looked at what the kind of visualizations that you typically would have in multimedia analytics. Well, most of the time when you see images in a visualization, it's just in a grid. That's the typical way you would organize your visualization. You can put it in a similarity space, so using methods like T-SNE or UMAP, that kind of methods, where images that are similar are also closely related in space. You can combine the two things, so you take things that are similar and put them in the same position, but you still show it in a grid, which is, of course, in terms of space, more efficient. You can use a kind of spreadsheet or table-like visualization, or you can make a thread-based visualization where you have something that is in the middle, that is your focus point, and you can see what kind of directions can I explore if I go into that space. What are you then going to do? So what are the tasks that are typical for multimedia analytics? Just exploring the data, trying to put structure to the data, just finding relevant items, searching. What you very often see in police-like applications, huge amounts of data, but you're only looking for tiny needles in this haystack. Can you do that in a proper manner? And we kind of found a method. We said, well, we put it on exploration search axis. Some of the tasks are more exploration-based, some of them are more search-based. So exploration, you don't know what you're looking for. In search, you have a very clear idea what you're looking for, and you're going back and forth between those two. And it turns out that if you look at it from a image analysis perspective, what you are doing there is basically categorization. So if you have search, you're basically looking for two categories, ones that are relevant for your task and the ones that are non-relevant. If you're doing a ranking. Basically what you get in Google or any other search system, you get a ranking of 20 elements. You basically want to have the best ones in this top 20. So still a categorization problem. So we come up with the term analytic categorization, so that all the tasks that you have there are in the end trying to do categorization and doing that in the best manner. The problem, or an interesting challenge, is that a human doesn't use a fixed set of categories. Getting insight, as I said, was a deep process. It was something that is building up over time. So while you're doing that, many of the categories that the user is employing are actually changing. And that's what we call the pragmatic gap. So a system has a very fixed idea of what categories are, and with the current foundation models, it's a bit more elaborate than that. They can take some context into account, but humans are far more flexible in how they use those categories and how they explore the data. And what you then need to do, if you have categorizations, if a human is going through the data and exploring interesting elements, what you typically see is they identify elements that are relevant for the category and elements that are non-relevant for the category, and the system can learn from those interactions. So based on those combinations of relevant and non-relevant, it can identify for images that you haven't seen, that the human hasn't seen, well, those are likely relevant for the task, for the category, and those are non-relevant. So you can make suggestions based on that. And this is the pipeline that we came up with. So you have your multimedia data, so the visual analytics paradigm that we had. You had those different visualizations that you could have. You have different interactive learning models, and the knowledge is captured in those categories. So at that time, we developed two example systems that were following that paradigm. So one is the fork browser, which has this thread-based perspective. This is a modern version of it, but where you have an image in the middle, that's your current element, and you're looking at different directions to explore things, and in that way go for your space. And whatever you see something on the screen and you select it, then the system knows, well, this one is important. And if you didn't select it, then the system also knows, well, most likely it's not important, so it can actually learn from that interaction. And based on that interaction, it also selects the proper new elements in your threads to explore. Second system we developed were multimedia pivot tables. Well, if people are familiar with Excel, they know the concept of pivot tables, but of course they don't work for image data or multimedia data. We took that idea and brought it into a spreadsheet for multimedia data. So integrating maps, integrating tag clouds, the images, all kind of automatic analysis in there. And the user can interact with it, can select elements, so you get this idea of, again, putting things in categories and putting things that are not selected in categories. And we made something that are called active buckets. So based on what the user has done with the system, it makes suggestions. Well, you said that those were relevant, so probably those are also relevant. Based on that, the system hopefully gives you interesting suggestions. So bringing it all together, and that's the final model that we have for multimedia analytics. So you see this pipeline that actually led into Sasha. Yep, into the model of Sasha, the more expanded version of the visual analytics paradigm, and having the model that we have developed. And we came to this new model where you see the same kind of components that are in the model by Sasha, but now made specific for the idea of multimedia, which is a bit different than the other things. So the search explore axis is an important component, but also how you build the model is different when you're doing multimedia analytics. Now I will show two systems that we have developed following this kind of new paradigm and this new idea of working with it. So the first one is the hypermatrix. So that is work that we did with the people in Constance in a European project with the police. And that is based on so-called hypergraphs. So what are hypergraphs? Well, I know everybody is familiar with using graphs. So you have nodes and you have connections between nodes. But very often, if you're describing a real-world phenomenon, it's not enough to just have relations between two elements. You need relations between multiple elements. You have groups in your data which you cannot describe using a graph. Well, hypergraphs do exactly that. You have nodes in the same way as a graph, but you can also have edges which have 3 elements, 10 elements, 20 elements, 1 element. So you have far more flexibility in defining your elements in the hypergraph. And we use that in this Stormfront problem, having topics that were, people that were describing their thoughts in text, and they were in different categories, in different topics. And what we aim to do is kind of finding whether people start to move into more radical topics. That was what the police was interested in. And we bring texts that are about the same topic, you put them in one hyper edge, and based on that you try to find other elements that are in there. This is how you learn a hypergraph representation, at least that's how we did it at that time. We by now have more advanced methods, but what is most important, you learn a representation, but you can actually interact with it. So what does the user do? The user can change things, can indicate hyper edges, well, elements in a hyper edge that might be in there or not be in there, so give feedback there. Then the system looks at what are the nodes and edges and hyper edges that are affected by the interaction of the user, and from there retrain the model, indicating, well, based on what you did here, it might also affect those nodes and those hyper edges. And you will see why we call that a ripple effect, because it's you have a local interaction, but it kind of spreads out more and more. If you give more interaction on the same point, it also spreads out to the other edges that you have. So this is the system that was developed, where you have the users here, the topics in which they are posting their material and what they are talking about there, and the matrix that you have here is how well is this user connected to a certain topic. And what we aim to do is to see whether some people are starting to put elements in topics that might be radical. And you let the user decide there. So the user can indicate, well, I see a topic here which I know this person has posted in, but for some reason the system has not identified it. So we can add that to the system, and based on that, it will start spreading out this information to the other edges. And you will see that in this matrix. So when you indicate something at some point, you will see other elements that also become darker because it also affects those hyper edges. And currently we're looking at how to do that for multimodal data. Another one, I already said, one of the other topics we work on are deepfake. Deepfake detection, video deepfake detection. So that's the Proto Explorer system, which is coming up very soon. Forensic experts, they look at deepfake detection by looking at things that are not completely right in the image, inconsistency in lighting. Those are the kind of things that people are using. What AI methods are currently doing to detect deepfakes, we kind of don't know. So that's one where you need a multimedia analytics system. So this is a deepfake detection model, which we took from literature. But what it does, it takes an input sequence and it uses prototypical elements to see, is this a fake or is this a non-fake video? Oh. So if you put those kind of videos into the system, what does it do? Well, it looks at the image and it compares this to prototypical elements that have been selected. So the system has selected prototypes, and it looks at a part of the image. You select that from the one that you want to know whether it's real or not, and it sees whether it looks more like real prototypes or that it looks more like fake prototypes. So based on that, it makes a decision. Well, in this one, it has almost everything is very positive that it is a real video, so the output would typically be real. And if you have this one, there are a lot of patches that are identified as probably more likely, more similar to fake prototypes than to real prototypes. So this is probably a fake image. And we have put that in this multimedia analytics model. So you see the same kind of things, but now twice. One, we have two visualizations. Now we'll go for the visualizations in a minute. And both have this same model, starting from the data, having a model, having a visualization, and leading to what in this case is trustworthy evidence in court. That's what we're aiming for. That the forensic expert can take this data, can take the result and say, well, this is the reason that I have identified this as being fake or real. So this is the one element, so the deepfake analysis itself. So you have the video that you are looking at. You have the prediction per frame. So if it is red, it means, well, most likely this is fake. The part in blue is how likely is it real. And you see the individual contributions of the prototypes. So you have those fake prototypes, you have those real prototypes, and you show over time how similar they are to this particular prototype. And then in the end, there's one score saying, well, for this video, I think it's real or it's not. But one important component, and that makes it interesting in the system, is that the user is actually able to change those prototypes. Because if the user feels, well, the system selected this prototype, but why? Why is it of interest? It's not something that I see in the image. And well, it's a bit hard to see, but you see on the right-hand side, you see a sign say landmark density. When we were building this system and showed it to experts, they actually said, well, the landmarks are not nicely distributed. The prototypes are not nicely distributed over the face. And we want to have prototypes everywhere. So the user can actually then select other prototypes that are more suited to actually have the mouth in there, and the eyes, and the chin, and everything. And that refinement, we make sure, and that's what we visualize, that the accuracy remains the same, but that the user can actually have more explainable prototypes that are better for giving it to putting it into court. I don't have time anymore, I think, so I will go to the conclusions. Sorry. Nope, I need this one. Quickly. So the only thing that I want to say, now with all those foundation models, things are changing. We are moving towards artificial general intelligence. You will see that term coming up a lot, where we try to be more and more intelligent, but we still need things like visualizations, because we're only capable of doing some of the tasks. There are a lot of difficult tasks that the systems are still far from being able to answer. So in the new models that we have, generative models, so foundation models that can generate data, create images, create videos, create text, ChatGPT, GPT-4, the visual part of GPT-4, Sora, all those kind of systems, they are needed in this whole pipeline. So summary, what have we done? We have a multimedia analytics model, which brings together multimedia analysis and visual analytics, and helps people to get insight in data. They've shown a number of systems that we can use based on the multimedia analytics paradigm. We have a number of new techniques that are relevant to work on, and the foundation models that have been around and will continue to be more and more elaborate over the coming years, and looked at several applications and data sets that we are currently looking at and try to see whether we can make an impact there. And with that, I would like to stop.
Professor Marcel Worring.